And this is my project name, Yarou. And our project today is the histopathologic cancer detection. So the project is originally in the form of a Kaggle competition, and data set is provided through this competition, and the target for our image classification is to identify whether center 32 by 32 patch contain at least 1 pixels of tumor tissue. And so since deep learning has been the state-of-the-art method for image classification and object detection, so we decided to choose learning as our basic structure for this problem. But due to the fact that so our data set is 96 by 96 pixels, and due to the fact that tumor tissues might only present in center 1 pixels, and it might be near a really larger object, so the target is kind of obscure. So we proposed a slight twist to the classic and traditional convolutional neural network structure. We propose a multi-scale approach this problem. So in the previous related works, the multi-scale approach has been utilized to solve a lot of real low resolutions and smaller feature detection and classification. For instance, one of the previous paper talked about the same issue, but they wanted, for instance, if you want to detect a mouse or a telephone in a really large image, a lot of the paper use this multi-scale approach, and their results appear to be very accurate. So this is why we decided to use multi-scale for our project. Yes.
Well, thanks, Yifan, and she talks about the introduction about the previous research and also the background of our project. And here is our project, and I will let you. I will talk to you about that. And first, we need to explore our data set a little bit. And first, let's say a random 6 samples for the banal cells. And here is it. Take a look at it. And then we will have a look at the cancer images, also a random sample. And we can find out it's very difficult for our normal people to find these cancer cells among these benign cells. That's why we need to teach the computer to detect this one for us. And then just look at this training sample, and we can find out there are a total 139 cells, and there are 89,000 cancer cells. And we can find out this data set is not very strictly balanced. The ratio is okay, so we will just use the data as its original format. And then we will go into the structure of this model, and this image can show us clearly. First, for our multi-scale scene structure, we use 3 parts of a convolutional and max pooling layers. For the first part, it's a 1 convolution, 1 max pooling. The second part, 1 convolution, 1 max pooling. And the third part, there is total 3 convolutions and 3 max pooling. And then we just speed up this part 1, part 2, part 3 together and flatten it, and then fix all these 3 image informations into 3 fully connection layers, and then use a softmax layer to have an output of 1 and 0. And because we know that we need to compare it with the baseline, so we're training another simple CNN as the baseline, and the previous 3 layers, 3 parts are the same with the multi-scale CNN. From here we can find out we only fit the part 3 into the 3 fully connection layers and then have the output of 0 and 1. And now let's look at this result. So here is our simple CNN result, and we only use like 1% of this training samples because too big, and we need to find out that whether this model will work or not. So we only use like 2,115 samples here, and we can find out the result that using the simple CNN model, it start converge at epoch 15. And then the final accuracy is about 78. And here is the arrow under the curve. Here is the loss function, and it's all start converge up at the epoch 15. And as for the multi-scale CNN here, we can find out that it converge more quickly. It start converge about around epoch 8 or 9. And of these 3 here. And also it has a more higher accuracy. It's about around 80% accuracy. So we can find out using these small training samples, the multi-scale CNN works much better than the simple CNN. And so we just confirm the previous research, and we find out this multi-scale CNN is working very good at detecting the small objects like a cancer tissue around all these large benign tissues. But we also find the problem that when we use a large scale data set, like the full 220,000 training data set, using all of these large data set, our model, the multi-scale model doesn't improve accuracy. It actually has the same accuracy as the simple CNN, and we thought that might be because all these training data set can offer enough information, so our model maybe not useful to just offer more information for this situation. And that's why we think that the multi-scale CNN model may just performs better when there's not enough training data set, when the training data set is very small. And also, because just like I said before, there's one problem with our data because it's not strictly balanced. We think that we may just improve the accuracy a little bit more when we just converge our data set to a 1-to-1 ratio, and that's our further research.
Now we'll take